In our last lecture, we were looking at what we called significant figures. And especially when we're talking about measured quantities, significant figures being then numbers that we measure that we can record justifiably. And we indicated that the reason there were some limitations to what we can record as far as data is because of such things as human error, also the measuring device calibration, and also the mechanical limitation of the measuring device itself. And we looked at a centigram balance and indicated that the best we could record a mass would be to the nearest hundredth of a gram, 0.01. And we want to take a look here just at another measuring device as an example then of this significant figures. This is a burette, something that we typically use for titrating acid and bases and that type. I want you to look here right in this area here, and I'll turn the burette a little bit, right between the 9 and the 10. Now those represent milliliter units, all right? So if we were to take a look, then we see that, we see that between the 9 and the 10, there are 10, if I can get this focused reasonably well, there are 10 small lines in between the two, meaning that we have marks at each 1/10 of a milliliter. All right? This is a fairly typical burette. Now I've drawn a little blue line in there, and if we were going to record this as our measured volume of solution in the burette, we see then that it falls someplace between 9 milliliters and 10 milliliters. So we know that it's at least 9 and it's less than 10, so we would write down a 9. And we see that it's less than half of the way. We see a halfway mark, so it's less than 9.5. As a matter of fact, if we look, we see that it falls between there, again, if we can get that in slightly in focus there, there's 9, 9.1, 0.2. It's between the 9.3 and the 9.4 mark on the burette. Now it's not 9.3, it's more than that, and it's not 9.4, it's less than that. We're certain that it's at least 9.3. So those are our two certain numbers. Remember, significant figures are all of the numbers that we are certain of plus one uncertain, or in other words, one number that we approximate. And so we would guess then that the line is about halfway between the two. So it's between 9.3 and 9.4. And so therefore we could justifiably write our volume down as 9.35 milliliters. Now the question is, once we have done that and recorded it, how many significant figures do we have in that measured quantity? 3. Remember our rules that we looked at yesterday, that all digits between 1 and 9 are significant figures. So we have 3 significant figures in that measured value. Now, we do have a super chemist, an analytical chemist that can read burettes much better than this, and we'll take a look at his work. This is the world famous chemical analyst. You probably recognize him a little bit, but he's reading his burette, which is the same as what we just looked at, to 5 decimal places. You see? In other words, he would call it 9.35 4, 2, 7, 6. 5 places after the decimal point. Now that's what we're meaning by limitation of the instrument. No matter how good the chemist is, reading this burette, and volume-wise, the best they can record is 9.3 something. The last number is the number that they have to interpret, and therefore they would record, and this is where we have some variability. If I read the volume on the burette, I might read it as 9.33. The next person reading it might read it as 9.36. That's the human part. Our eye levels might be slightly different at the way we're looking at the burette, and therefore the number would be different. But for somebody to say that they could read a burette to 5 decimal places, in other words, this super chemist here, 9.3xxxx, obviously is ridiculous. We're beyond the limitation that we can practically use our measuring device. Now, if we have a burette that has better markings, smaller tube, more lines in between, then we might be able to even get a 3rd place. But this is a typical acid-base burette we're looking at here, which is the same as what I'm looking at here. The tip has been removed, but it's the bulk of the tube is the same. So it's important to remember, both when we're measuring quantities in the lab, as many of you will be doing next week again in experiment number 2, you will be restricted to recording data, measured quantities based on the measuring device that you're using. If you're using a centigram balance, the best you can weigh is to the nearest 100th of a gram. All right, and so on. Now we also looked at the rules for determining significant figures in a written number. That's assuming somebody has measured it for us, and we're going to then determine the number of significant figures. And for just a quick review of those rules that we did yesterday, we'll apply them to these 5 numbers right here, which, by the way, is question number 5 at the end of chapter 1. We look at the first one, and the correct answer is that there are 4 significant figures in this number. And the rules for that is that, first of all digits are significant, but the second rule was that all zeros falling between digits are significant. So both of those zeros are actually measured quantities. It is 300.6. So those 2 zeros are significant. They are measured quantities. We look at the second number, which in this case is written in scientific notation, as we mentioned in the previous lecture, writing large and small numbers by using a power of 10 scientific notation. Again, here then we would say in this particular number we have 3 significant figures. Because again, this one is, and this one is, and the 0 between digits is also significant. We get to this one, and the correct answer is 4. Now we will say why it's 4. First of all zeros preceding a decimal or following a decimal which is not preceded by a digit, so this is not, all of those zeros are not significant. The other statement is that these zeros, which follow digits after a decimal point, are significant. I believe that's the 4th rule. But again, the best way to look at that number to see significant figures is to rewrite it in scientific notation. If we were to move the decimal point here, we would then rewrite this number as 3.400 times 10 to the minus 3, because we moved it 3 places. Now we can see more easily that in fact those four numbers are measured and significant values. The next one is quite obvious. It's four significant figures because all digits are significant. The next one is maybe also somewhat obvious. We have 7 significant figures in that one because we do have a digit in front of the decimal, so therefore any number or 0 after that is significant. So all of these are in fact significant figures for that number. Anyone have a question on just looking at a measured quantity and determining the number of significant figures? All right. Then, keeping that in mind, we said, now if we make some calculated values using measured quantities, our answer is also affected by those number of significant figures. We said previously that our answer cannot be better than the poorest number that we have used if we're talking about multiplying and dividing. Let's look at a couple of example problems dealing with that. And I'm looking at problem number 9 in your text. And let's look at 9 part A. It asks us to multiply 3.084 times 9.6. So we take the calculator and we punch in then our two numbers. So 9.6, whoops, I have a 4 in there. 9.6 times 3.084. And the numeric value that I get at that point is 29.6064. That's what the calculator display shows. Now, the question is, however, what should my answer really be shown as? Well, the question is, how many significant figures are we justified in our answer? I heard 2. Very good. We have 4 in this number. We have 2 in this number. We're limited to 2 significant figures in our answer. Now, that means then that we start with this number and we say, this one's significant, this one's significant. That's as far as we can go. Now we have to look at the rules of rounding off. We're not just going to arbitrarily throw everything away after that dashed line. We're going to look to see if in fact we need to round up or round down the number in front of it. So in this particular case then, we would have to round up because this is greater than 5, and our answer would be 30. Now 30 doesn't look real good as far as significant figures, however, because that 0 after the 3 is always somewhat questionable. But if we write it in scientific notation, anyone looking at our number will know that we mean 2 significant figures. So I'm going to rewrite this then, and I'm going to call it 3.0 times 10 to the 1 power, or just times 10 you could say. All right? Now notice when I write it as 3.0, there is no doubt the 0 after the decimal preceded by a digit is a significant figure. Back to the rules of significant figures. Okay? And so we then have displayed the answer in the correct number of significant figures and in scientific notation. Let's look at the next part of that problem, which is a division. In this case, we're going to divide the number 5.2 by 4763. And as I say, this is problem number 9 at the end of the chapter in the problem set. So 5.2 divided by 4,763. We get a display in a calculator. Now, if your calculator has exponential notation, it will automatically write the number for you in scientific notation if it is small or very large. So that's the advantage. That's why I said it is good to have that on your calculator. This is what my calculator shows. 1.0917489 times 10 to the negative third. But I don't want you to write that on a test. I don't want you to write that in a lab report just because the calculator says. The calculator is pretty stupid. I mean, it'll give us numbers, but it doesn't know anything about significant figures. And if it doesn't, then it's going to give every number that it can that comes up. But we don't record it that way. How many numbers should we have? How many significant figures should we have in our answer? 2. Once again, because our poorest number we're using has 2 significant figures. 5.2 has 2, and of course 4763 has 4. Our answer is limited to 2. So, again, we count over 2 places. We'll look at a line right there. What is after the line, of course, obviously is bigger than a 5, meaning that we're going to round the number up 1 step in front. And so we're going to rewrite this then and express it as 1.1 times 10 to the negative third. Only the number has anything to do with significant figures. The 10 to the minus third is merely locating the decimal point. Has nothing to do with measured quantities. So our answer properly written, 1.1 times 10 to the minus third. All right? So as you go through working on problem sets and laboratory reports, be sure to pay attention to significant figures. Now, if we're adding and subtracting, we mentioned that we have a slightly different set of rules to follow. In the previous lecture, we said that if we're adding or subtracting, we look at only the things after the decimal point, and we keep the number of positions after the decimal point equal to the number of positions of the smallest, or again, poorest number that we're using. Notice here we have 3 places after the decimal in that number, but we have only 2 after this one. So our answer should have only 2 places after the decimal point. Now, we don't just arbitrarily throw away this 6 then. First we do the math, then we change it to the proper number of significant figures. So subtracting this, we would have a 6, and 9 from 7 would give us an 8, and we borrowed 1, so 7 minus 1 would be a 6, and a 2. So we have 2.686 just by doing the mechanics. Now, we're only allowed 2 places after the decimal, so we would look at it that way. And seeing that the 6 is greater than 5, our final answer should be written as 2.69 for an answer. Again, let me emphasize that in addition and subtraction, our answer may have more or less significant figures in it than the poorest number involved in the calculation. Notice we had 4 significant figures in the first number, 2 in the second. If it were multiplying or dividing, we would have been limited to 2 significant figures. But in addition and subtraction, it is possible to come up with more places, more significant figures than the poorest number we're using. We ended up with an answer, and a correct, justifiable answer of 3 significant figures, even though we had a number in there that had only 2. Now, what happens if we have a problem that has both multiplying and dividing and adding and subtracting in? Well, we use then our mathematical procedure that we do then the adding and subtracting first. We have to add that number, those 2 numbers, before we can do the division. So we will add or subtract, and then mathematically we'll do the second step, which would be the division. And each of the processes must follow the rules for that particular step. In other words, we're going to add the two numbers, we're going to follow the rules of addition. Then we're going to divide, and we're going to follow the rules of division as far as significant figures. I think that I saw a question, or did I answer it? Okay, question.
C, would you not round that up to be 2.7? Or would you leave it like that?
The question was on part C, would I round it to 2.70? And the answer is no, I would have no reason to round it to 2.70. We've already rounded up the 8 to a 9 because the 6 occurred after it. But that's as far as we would go. We would keep it as 2.69. All right? Now, on to this last one then. I said we're first going to take care of the first part. So what we're going to really be doing here is we're going to say 4.23 plus 9.65. And we'll add those together, and we get 13.88, and all of those are allowable because we have two places after the decimal in both numbers. So now our problem goes 13.88 divided by 7.089. So I do that on my calculator. 13.88 divided by 7.089. And we get an answer of 1. Okay, I'm breaking off. This is following that one. 1.957963. Calculator. How many significant figures should I have in my final answer? I heard somebody say 3. I see somebody signaling 4. And I'll get to your question in a second in the back. Okay? 4 is correct. Notice that when we're doing the division, how many significant figures in the number at the top? 4. How many in the number in the bottom? 4. We're justified in 4. Remember, you take each step individually. The 13.88 is correct using the rules for addition. And that's the number then that we're dividing. So even though we started out with two numbers back up here then that had 3 significant figures in them, the two numbers we were adding, our final answer can have 4 because of the rules. So we would go over 4. And our final answer would be 1.958 would be the correct number. Now, let me get the question in the back there. Okay. Well, that's all right. You can do that one, and I did this one. All right. Now, one of the things that I do throughout the course, let me warn you of that, is I often will make an intentional error in solving a problem just to see if you're awake. You see, because otherwise you just write down everything I do and I say, does that make sense? And everybody goes, yeah. Well, it won't always make sense. All right, I copied this down before I came to class and I made a mistake. I made a mistake in writing the number down. Now, I'll just let you work the other one. That's fine. With the, what did you say it was? 42.03 or 42.3? Okay, 42.3. We would get a different set of numbers then. And we would end up, in that case, I believe we'll end up with an answer really of 3 significant figures. Okay? But the main thing here is to understand the rules that we're following. We must follow the rules that apply to that mathematical process that we are using. All right, one more question back there.
On this, on D, it was subtraction on the top line and still then division. Do you follow the subtraction rules only for the top line and then switch over to the division rules?
That is correct. You followed, the question was, if the top had been subtraction instead of addition, would we follow the subtraction rules first, and get that answer and then go to the division rules, that is correct. You do that mathematical function using that set of rules, and then you go on to the next step. If you had 5 different steps, each step you have to apply whatever rule it is that you're using at that step, okay, until you get to a final answer. All right. Well, let's continue on here then. Now, we also talked about, well, I guess we haven't talked about, I'm sorry. In solving problems, one of the techniques that we use, there are many ways of setting up problems, but typically for our problem solving, the method that we're going to use is called unit or dimensional analysis. And the whole process is merely to say, what is it that we're solving for? What's the question? When I read a problem, what do I want to get for a final answer? And we put that unit down on the left-hand side. And then we put an equal sign, and then we say, now what measured quantity do we have to work from? And we record that. And the whole process of setting up the problem then is to find what we call conversion factors, to convert the measured number to the unit that we're asking for. This probably makes more sense as I do, or hopefully as I do a couple of sample problems. Well, let's look at problem number 11 at the back of the book, assuming that I wrote it down correctly. The question is, if we have 95.6 centigrams, how many kilograms do we have? So, using dimensional analysis then, or unit analysis, what we want to solve for is kilograms. That's my unknown. And what is my measured quantity? 95.6 centigrams. Now, I'm going to need to find some conversion factors. In this case, we're looking in the metric system. So I need to find some conversion factor that will allow me to change from centigrams to kilograms. Well, maybe I don't have directly one conversion factor that will do it. We may have to put in a couple. Now, when we talk about conversion factors, these are numerical relationships. And the thing to remember is that they can be written either way. We can say 60 miles per hour, or we can say 1 hour per 60 miles. We can say 12 inches per foot, or 1 foot per 12 inches. So we can use conversion factors in whichever form we need to get the units that we want. What I'm going to do here is I'm going to first of all convert from centigrams to grams. Okay? So we have 95.6 centigrams multiplied by, all right, how many, 1 gram contains how many centigrams? Anyone? Well, we could go back and look at that metric table in the book if we didn't remember. But centi is 1/100th, so there would be 100 centigrams in a gram. If we do that, notice our units, centigrams, have now canceled. So now really we're asking the question, how do we convert from grams to kilograms? We look for another conversion factor. In this case, we know that kilo stands for the prefix of what? 1,000. So 1 kilogram contains how many grams? 1,000. Or we can say 1,000 grams per 1 kilogram. We can use it in either fashion that we want. Well, we're going to multiply now by 1 kilogram per 1,000 grams. Notice now our grams will cancel. What do we have for a final unit at this point? What's the only unit left on the right-hand side of the problem right now? Kilograms. What did we ask for on the left-hand side of the problem? Kilograms. When the units become the same, the problem has been correctly set up. And we're going to use this technique for solving stoichiometric problems for balanced chemical equations. We're going to use this for all sorts of chemical problem solving. We ask what is it we want What did we measure? How do we get from there back to the units that we wanted? That's all we have to do, are look for appropriate conversion factors. So, in this case then, we now have completed the unit part of it. We would now have the mathematics part of it, and we would end up with an answer then of 95.6 divided by 1,000 times 100, or 1 times 10 to the 5th, or, and I didn't leave myself much room here, so let me jump down here, 95.6 divided by 1 times 10 to the 5th would be equal to 95.6 times 10 to the minus 5th kilograms. Now that is not written in scientific notation, because scientific notation we have only one number preceding the decimal. That answer's right. That's one way to write it. Or we could write it 9.56 times 10 to the negative 4 kilograms. And that would be our final answer. Unit analysis. Well, let's look at another metric conversion here, part C of that same question. The question on part C in number 11 is, if we have 4.2 times 10 to the minus 3 milliliters, how many deciliters do we have? All right. Again, there is more than one way to approach the problem. You might have chosen a different set of conversion factors in the first step. Or you might have written it as 0.01 gram per 1 centigram. That would be all right. So just because I write it one way does not mean that you would necessarily choose the same. But as long as we have the units on the left and the right the same, we both have set the problem up correctly. We want deciliters. And we're starting with 4.2 times 10 to the minus 3 milliliters. Now, whenever we're working the metric, we can always go back through the key unit, the 1 unit. So in other words, what I could do is go from milliliters to liters, and then liters to deciliters. We can do it that way. There would be other ways to do it. But this way we're focusing on going back to the base unit. So what are we going to say here? 1 liter contains how many milliliters? 1,000, or 1 times 10 to the 3rd. So now our milliliter units have canceled. Now we're at liters, but that's not what we want. We want deciliters. And deci stands for 1/10. So we now have to put a conversion factor in here for that. And we can say then that there are 10 deciliters per 1 liter. Or we could also write that there is 1 deciliter per 0.1 liter. A deciliter is a tenth of a liter. We could write it that way. Or we can write that there are 10 deciliters in 1 liter. Again, doesn't make any difference. Our number will come out the same. So at this point, we see that we ask for deciliter. Notice that all of the units are gone on the right-hand side except for deciliters. Therefore, the problem is set up correctly. All right? Now, all we have to do is the mathematics. In this particular case, let's see, we would end up with 10 to the minus 6, 10 to the minus 7. So 4.2 times 10 to the minus 7 deciliters would be our final answer. I'm sure you can punch the numbers in once we have the problem set up correctly. All right? Yes, question?
Yes, I'm making a mistake somewhere, because wouldn't the negative 3 and the 3, oh no, because the negative 3 would go on the bottom.
Right. Okay. Good question, and she answered it herself. So, okay, it was a math question. Let's look at number 13, part A, doing the same type of thing, using unit analysis. It gives us some information about a piece of solid metal. It gives us the mass, it gives us the volume in cubic centimeters. It says calculate the density. Now, from previous lecture, we said that density is defined as the mass of an object divided by its volume. And if it's a solid, we said that the units that we use are grams over cubic centimeters. So what we want in our answer unit-wise is grams divided by cubic centimeters. Well, this time we really don't even need to find a conversion factor. All we need to do is put our two numbers in the proper place. We want to put our grams on top, and we want to put our cubic centimeters on the bottom, and that will give us the units that we know that we need for density. So we're going to go ahead then and put in 137.92 grams over 57.3 centimeters cubed. And we go ahead and plug that into our calculator. 137.92 divided by 57.3. We get an answer then. How many significant figures should we have in the answer? 3, correct. We have 5 in the top one, 3 in the bottom one. We should have only 3 in division. And our final answer would be 2.4. It's 406, but we're only going to have 3 significant figures, so the number after the 0 is greater than 5, so 2.41 grams over centimeter cubed. Question, yes?
On C, should that be 4.2 times 10 to the negative 5? Wouldn't the 3 come up to be negative 3, and then be negative 6, and that 10 is positive?
Oh, yes, thank you. Okay, very good. 10 to the minus 3 divided by 10 to the third would be 10 to the minus 6th. 10 to the minus 6 times 10 would give us 10 to the minus 5th. Okay? Very good. Well, I put one out there, and somebody finally caught it. All right? 10 to the minus 5th is correct. Any questions on this part here on significant figures? Okay. Let's look at problem number 15. It says we have a gas. We have 38.5 liters of the gas, and we know the density of the gas. And the question says how many grams? What mass do we have? So our units that we're solving for is grams. Our measured quantity is 38.5 liters. Question is, how are we going to change? What conversion factor can we find that allows us to change then from liters to mass? And of course, if we look, we see that we do have a mass to volume relationship in the density. So if we use the density as a conversion factor in this case, again paying close attention to units, if we were to multiply by 3.165 gram over 1 liter, we notice that the liters will cancel unit-wise, and we're left with grams, and that's what we wanted. And so now we would do the mathematical number and have our answer. Any questions on that one? The next one gives us a mass of helium. Ask for the liter, what volume. So this time we're setting up liters. And our measured quantity is 3.26 times 10 to the minus 1 grams. Now, we don't have any other information given in the problem, but preceding the problems, it indicates that we can find information in the text. So if we go back in the text to the table on densities of some common elements that we had, we can find that the density of helium is 0.18 gram per liter. That's the density of helium. That gives us then a conversion factor relating mass and liters. Now, we quickly throw that in because we know what we're doing here. So we say 0.18 gram of helium over 1 liter of helium, and we calculate our answer. And we're wrong. Why are we wrong? I mean, did we not use the correct density? Yeah, we used the correct density. But look at the units on the right-hand side. What are the units on the right-hand side of the problem? What would the units be? Don't worry about the number. We would have grams times grams. We would have grams squared over liter. Is that what we asked for? No. That immediately tells us we've set the problem up incorrectly. What we set up incorrectly is we used the conversion factor here. Correct conversion factor, but used in the wrong way. If I were to go back down here, and I'll give myself a little room again, 3.26 times 10 to the minus 1 grams multiplied by 1 liter of helium over 0.18 gram of helium, we in fact now see that the grams do cancel, and we have left the units of liters. So a conversion factor can be correct, but it must also be correctly inserted into the problem. Okay? All right. Any questions on this concept of using unit analysis for solving problems? We're going to be doing a lot of problems. We're going to set up a lot of problems in this fashion.